All right, so the first thing you're going to see is a person about 1950, maybe something around there. He did a song, and let's see if I can see this. Oh, not that one. Okay. All right. Anyway, this is a person around 1950 or something made this song. It's probably one of the more famous songs about the elements. And I know you didn't think there were any famous songs about the elements, but I'll start this again. This should be the words you have in front of you. Okay. So here we go. Here's how you can study. If you want, you can study for your final on Tuesday. All right, you ready? As soon as that thing comes up to speed here. I'll show you a different one than I showed the other class.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, radon, xenon, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Ooh, what do you think? Does that help you? Okay. I want to show you one more here. Yeah. Do you know who this guy is? Have you ever seen this guy?
No.
Give a big shout if you know who Tom Lehrer is.
You know who he is? Okay, just want to make sure. He didn't have to do this. He took a big chance to me when you go on a late night talk show. But here's what he did.
Yes, no, over there. You have to be more excited.
Okay, so Tom Lehrer, in my opinion, is the cleverest and funniest man of the 20th century, and he's kind of my hero. And he wrote a song called The Elements, because he was a scientist, and it's the name of every element in the periodic table. And that's my party piece. It's quite long, so do stop me if you just get bored.
Okay.
I will. This kept me up last night. I was so nervous about doing this.
Do I feel bad now?
No.
Okay, so.
There's antimony, arsenic, aluminum, selenium, hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, hafnium, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, silver, and samarium, bismuth, bromine, lithium, iridium, and barium. Let's start the next verse. There's holmium, helium, and hafnium, and erbium, phosphorus, and francium, and fluorine, and terbium, and manganese, and mercury, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium. There's lead, praseodymium, platinum, plutonium, palladium, lithium, potassium, polonium, and tantalum, technetium,
we think it's
titanium,
mind
thorium,
doing.
and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, radon, neodymium, and argon. Hold on, quiet. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, radon, neon, krypton, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. Now,
All right. Anyway, you can do it. I won't show you all these. You can sit here for an hour and look at all these. There's remember the guy from Big Bang Theory? He did it too on a late night talk show. But I'll show you one more. This is a different song, and it has all 118 elements on it, and it only lasts for a couple of minutes. So I kind of like this one too. And then that'll be it for the songs.
And now,
ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, and oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the sign, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, and argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, the whole gas is stable, halogens and alkali react aggressively. Each period will see new outer shell, electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel, coin together, copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine, then will krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun, lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62, samarium, europium, gadolinium, and terbium, dysprosium, chromium, erbium, thulium, ytterbium, lutetium, hafnium, tantalum, tungsten, then boron, rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead is good for your tummy, polonium, astatine would not be yummy, radon, and cesium will last a little time, radium, then actinize and adenine. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shell, electrons are to the right, actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, titanium, fermium, aluminum, nobelium, lawrencium, rutherfordium, rubidium, supercium, boreum, lithium, mercurium, obsidium, arcanium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and organesson, and then we're done.
Are you okay with that? Good. Wow, I just got here the elements of the periodic table 3 times. All right, if you flip this paper over, you'll see some really bad puns. I did not write these. I usually write fairly good puns. Of course, it has nothing to do with me, but anyway, some of these puns, what do you think? Do you think you know any of these? Let's take a look at, let me get one here. All right, which one do you think? They agree that?
I know 1 through 6.
Wow, all right, what's one?
Helium.
All right, I would take 2 answers on number 1. They helium, or they what? What else might they do? Curium. Curium. Okay, what's say number 2? They agree? Copper. 3.
Argon.
Ah, that's a hard one. Have went, argon. Ah, that's a good one. Next one.
Barium.
What do you got?
Barium.
Barium. You got the next one?
Yeah.
What is it?
Boron.
Yes, keep boron. Boron. Man, you're good at these. 6.
Cesium.
What?
Cesium.
Cesium. Yeah. Man, nobody else got. That's really good. Anybody got another one? Which one?
Number 9 is iron.
9. Yes, the precious earth, iron. Yes.
And number 11, is it zinc?
11 is what?
Zinc.
Yes, zinc. Instead of zinc. Anybody, you got another one?
It's 28 plutonium.
20 what?
28.
Wait, I gotta go down here. 28, I'm old enough to know who Mickey Mouse's dog is. What do you have?
Plutonium.
That's right, Pluto. How'd you know that? You knew that. Pluto is plutonium. Another one. You guys are good. I like when you would be. I like some of these are kind of bad. Like look at number 36. The opposite of hot. Gold. See, I don't think that's. See, it's so cold. Gold. So I didn't make these up. It's kind of fun. Anybody got another one? A couple more. How about a couple more? '24. Anybody know about that? Anybody watch rodeos?
What's a steer?
Number 24 says, what do you have to do before you brand a steer?
Manganese.
You ever see that where they go and they jump off the horse and take their legs and go like this? Then the legs are all together, then they brand them? What do you think?
Number 12.
What is it?
Is it Cali?
No. Starts with an E. Starts with an E.
Huh?
Starts with an E. EU.
European.
European. Okay. Which one? Yes, because the ship's kitchen, did you say it?
So I said number 12.
Oh, okay, I was talking about another one, sorry. What do you have, galleon? Okay, the ship's kitchen is called a galley. Galleon. 13. We got. We got
Lead.
E. So what is it?
Easy. Magnesium.
Maybe. Manganese. Manganese, okay. 7 is easy.
Coal.
What's chromium times a half? I mean times 0.5. Oops, I gave it away. Hafnium. What's another one?
Number 15.
15. What is that one?
Rhodium.
Yes, rhodium. You wouldn't know number 30 because that's a real famous advertising, and it was about a perfume. It said, blank them anything but give them our page. Has anybody ever heard that advertisement? Okay, that your grandparents would know that one, okay? It was promise them anything but give them our page. So it'd be Prometheum. I like 32. How do you think about that one? What? I know, but what's the element? No. Oh, it could have been California, but it's a view by a boy whose name is Cal. A view.
California.
Calcium.
Oh.
Calcium.
What's 23?
23. I don't remember that one. Darn, what do they call that?
Reading.
This is the Scandinavian countries. So Scandium. Yeah, Scandinavia. 18 is kind of a bad one, but
The wrong.
18?
Hydrogen.
18 is one of the first 20 elements. It's in the first 10.
Hydrogen.
Carbon. Okay. All right, I think that's enough of that. Anyway, if you want to play around with this over the weekend, just kind of play around again. All right, so when is our big element quiz? Tuesday. It's not a quiz anymore. Now it's just like a test, isn't it? All right, now, next. We have some people who haven't told us about their experiment, so we have some scientists, and we want to get them up there, and okay. All right, let's come on up, and let's have a person come up, and somebody on deck. Okay, now, it's very important that it has to be quiet enough so I can hear. I want to hear every single thing they said. And I might even have some questions for them, so everybody be quiet as you can. It's wherever you put them. You should, remember you were supposed to put them back where you normally put them?
This is a different class. You don't need them. I know, I just want to.
Oh, I told get people to put them back here where they usually kept it. All right, you guys have a seat, okay? Unless you're looking for your thing. Hang on just a minute. Got it? What's going on here? All right, Taylor, I'm ready.
Okay. I'm Taylor, and my first observation was the wax on the top of the white candle started to melt about 10 seconds after I lit it. The flame turned bright orange and yellow at the top and purple at the bottom.
Did you ever think about why would the flame have different colors to it?
I'm gonna guess because like the heat is different, so like maybe like
Because what?
the heat is like different, so maybe like the purple is like hotter and like the
Maybe different amounts of heat, you think?
yeah. It's like
What do you think about that? Could it be, are the different places, you think that some parts of the flame are hotter than others? Okay, another observation.
I got 2 candles. I put the side of one up to the other candle. When the side of the candle touched the flame, a circle of black speckles appeared on the candle and wax melted off.
So the black speckles are not there to begin with, but then you put them on there and you saw black speckles.
Mhm.
Did anybody else do that?
Yeah, I did that.
Did you see the same thing? All right. Did you get black smoke at all?
I don't remember.
Okay. Let's experiment.
My experiment is I wanted to see the hottest like range like around the flame, and so I got like a piece of paper and like held it up to the flame, and I noticed that on the sides, like when I put my paper up to the side of the candle, it only burned when I touched it to the flame, and then when I put the paper on the top of the flame, it like caught fire without me touching like the fire. And then so I decided that the top was probably the most hottest part.
Highest temperature?
Yeah.
What was your distance on the top? How far away, how close, how far away and it's still caught on fire?
On the top,
Yeah.
I don't know. It was like probably a few like millimeters,
So millimeters are
like really small. Like
Okay, and what about the sides?
on the sides, I had to like touch the paper to the flame to make it.
It had to be that close, okay. Usually, on the top, did anybody else do this one? Usually on the top, I would say, even if you're like this close, that far away, that's like 20 or 30 millimeters. But it wasn't like that for you, you thought it was only a few millimeters?
Maybe like I don't remember.
Is this paper catching on fire?
Yeah, like a little piece of paper.
Okay,
I don't-
that's interesting.
I don't know.
All right, what do you think? Questions? Thank you. You can put that back down.
I'm Alani. So my first observation was that when I lit the candle, the flame started out really small, and then after about 10 seconds it grew bigger, and then after about 1 minute and 30 seconds it blew out, and I just thought that was kind of strange because I can't remember, but I don't think anybody was walking by and like nobody else blew it out, so it just went out on its own. And then at some point I relit the wick and the flame started out small again, and I'm also not quite sure like the time, but when I looked back the flame had grown really big, so.
So you're talking about the one where you blow it out and relight it with the smoke? Or you mean just blow it out and just relight the wick?
Yeah.
Ah, all right, so it took so small to start out with, and then it takes a little while to get back, okay. What do you think? What do you think about that? Do you have an idea about why it would start small and get bigger?
I was thinking maybe because the wick was small, and then as it burned, I don't know, there was more wick for it.
Did that happen? Did you see the wick actually seem to get bigger when you burn longer? Oh, I need to check. And sometimes scientists will do that, come up with a question, they'll say, I didn't look at that. And they'll go back and do it. I know it, for your experiment, right?
My experiment was kind of the same as Taylor's. I wanted to see if if a piece of paper could burn without touching the flame. like how hot the flame would be before it would burn. So I took 4 identical pieces of paper and I moved them, I held them at different
30 seconds?
sections of the flame. And
It says at 9.28 seconds, it crumbled and fell apart.
yeah,
The paper did?
yeah, that piece of paper was, I held directly like in the flame. No, wait, that was the wrong one, sorry.
See if you can summarize it for me. All right, let's say when you put it on the top of the flame, what do you think? What happened there? How far away before it caught fire?
It was almost right on top of it, or like touching the
Really?
flame.
So you're saying you had to be right on top of the flame before it catches on fire? That's interesting. I've never heard that. Okay, go ahead. And on the sides?
It didn't burn. I held it at the very edge of the side of the candle, and it never burnt or
Oh,
ever
really?
caught on fire. And then when I held it underneath the wick, it only burned when I touched the flame.
So under the wick, under the flame, you mean, you could be all the way underneath it and it doesn't catch fire until you actually touch it. All right, what do you think about that? Fire itself was hot enough, wasn't it? And Kathy, you went yesterday?
Yeah, I know,
He's up there. Oh, Aiden, all right, never mind. No, Aiden.
Aiden went, Sean
He went.
didn't go.
That's everybody, I think, that.
I don't think Luke didn't go. Yeah, Luke did. Luke did not go.
I did go yesterday.
Luke went.
I don't remember.
I have Luke.
I don't believe you went.
I did.
I don't remember. Well, if he did, I wanna hear it. I need to hear it.
All right, what I'm gonna do is, I'm gonna show you a very short video. And what the guy did is, he's a really smart PhD guy. He's a biochemistry, biomolecular. And what he did is he took some of the lectures from Michael Faraday. Michael Faraday gave Christmas lectures to teenagers. He wanted to get them interested in science. And he took some, he's gonna read from Faraday's actual lectures that he gave. And so he's gonna do some demonstrations too, and that'll be it for today. But let me get that ready for you. We're gonna start learning about how a candle works. Right now, all you know is you tried to discover something, didn't you? Some of you did. Some of you did discover some things, and some of you are not any more certain about the candle than you were before. Uh-oh, what happened? No, what happened to, I didn't know I erased it. Sorry, hold on, hang on just a minute. You see Faraday's experiments? Yeah, there. It's number 1. Yeah, here it is. Sorry. Hey, pay attention, okay? All right, everybody, pay attention.
I will tell you in 5 lectures the chemical history of a candle. There is not a law under which any part of the universe is governed which does not come into play and is touched upon in the chemistry of a candle. There is no better, there is no more open door by which you can enter into the study of science than by considering the physical phenomena of a candle. I trust, therefore, I shall not disappoint you in choosing this for my subject rather than any newer topic which could not be better.
You have to pay
even
attention
so
to this
good.
or I'm wasting time, okay?
Now as to the light of the candle. Notice that when the flame runs down the wick to the wax, it gets extinguished, but it goes on burning in the part above. Now, I have no doubt you will ask, how is it that the wax, which will not burn of itself, gets up to the top of the wick where it will burn? We shall presently examine that, but there is a much more wonderful thing about the burning of a candle than this. You have here a solid substance, the fuel, with no vessel to contain it. And how is it that this can get up to the place where the flame is? How is it that this solid gets there, it not being a fluid? Or when it's made of fluid, then how is it that it keeps together? This is a wonderful thing about a candle. You see that a beautiful cup is formed. As the air comes to the candle, it moves upwards by the force of current which the heat of the candle produces. And it so cools all the sides of the wax as to keep the edge much cooler than the part within. The part within melts by the flame that runs down the wick as far as it can go before it's extinguished, but the part on the outside does not melt. The same force of gravity which holds worlds together holds this fluid in a horizontal position, and if the cup be not horizontal, of course the fluid will run away in guttering. You see therefore that the cup is formed by this beautifully, regularly ascending current of air playing upon all sides, which keeps the exterior of the candle cool. No fuel would serve for a candle which has not the property of giving this cup. These beautiful candles, which are irregular and intermittent in their shape, cannot have that nicely formed edge to the cup, which is the great beauty in a candle. I hope you will now see that the perfection of a process, that is its utility, is the better point of beauty about it. It is not the best looking thing, but the best acting thing, which is the most advantageous to us. These good-looking candles are bad burning.
Thomas.
There is guttering because of the irregularity of the stream of air and the badness of the cup which is formed thereby. You may see some pretty examples, and I trust you will notice these instances of the action of the ascending current when you have a little gutter running down the side of a candle, making it thicker there than it is elsewhere. As the candle goes on burning, it keeps its place and forms a little pillar sticking up by the side because as it rises above the rest of the fuel or wax, the air gets better around it and it is more cooled and better able to resist the action of the heat at a little distance. Now, the great mistakes and faults with regard to candles, as in many other things, often brings with them instruction which we should not receive if they had not occurred. We come here to be scientists, and I hope you will always remember that whenever a result happens, especially if it be new, you should say, what is the cause? Why does it occur? And you will in the course of time find out the reason. Then there's another point about these candles which will answer a question, that is as to the way in which the fluid gets out of the cup, up the wick, and into the place of combustion. You see that the flames on these burning wicks do not run down to the wax and melt it all away, but keep to their own right place. They are fenced off from the fluid below and do not encroach on the cup at the sides. I cannot imagine a more beautiful example than the condition of adjustment under which a candle makes one part subserve to the other to the very end of its action. A combustible thing like that, burning away gradually, never being intruded upon by the flame, is a very beautiful sight, especially when you come to learn what a vigorous thing flame is, what power it has of destroying the wax itself when it gets hold of it, and of disturbing its proper form if it comes only too near.
Let me stop there for a minute. Had you considered the idea that that flame never does touch the candle itself? Have you considered the idea that the flame never touches that little pool of wax? So, what's burning? What do you think is burning?
The wood.
The wick? Did any of you, I know you did any of you take a wick away from the candle and burn it? How long did that last? Not long at all. So if that's the case, why doesn't this wick burn up very, very quickly? And that's the kind of thing I want you to do. I was hoping that you would discover certain things, and I'm going to be telling you what's going on after that. So here we go.
But how does the flame get a hold of the fuel? Capillary action conveys the fuel to the part where combustion goes on, and it is deposited there, not in a careless way, but very beautifully in the very midst of the center of action which takes place around it. Now, I'm going to give you two instances of capillary action. It is that kind of action or attraction which makes two things that do not dissolve in each other still hold together. When you wash your hands, you take a towel to wipe off the water. And it is by that kind of wetting or that kind of attraction which makes the towel become wet with water that the wick is made wet with the wax. If you throw the towel over the side of the basin, before long it will draw the water out of the basin like the wick draws the wax out of the candle. Let me show you another application of the same principle. You see this hollow glass tube filled with table salt. I'll fill the dish with some alcohol colored with red food coloring. You see the fluid rising through the salt. There being no pores in the glass, the fluid cannot go in that direction, but must pass through its length.
You know, so
Already
there
the
wasn't a
fluid is
real
at the
wick
top of the
there,
tube.
but
Now
they
I
did
can
blow
light
up,
it
didn't
and
they?
make it serve as a candle. The fluid has risen by the capillary action of the salt, just as it does through the wick in the candle. Now, the only reason why the candle does not burn all down the sides of the wick is that the melted wax extinguishes the flame. You know that a candle, if turned upside down so as to allow the fuel to run upon the wick, will be put out. The reason is that the flame has not had time to make the fuel hot enough to burn as it does above, where it is carried in small quantities into the wick and has all the effect of the heat exercised upon it. There's another condition which you must learn as regards the candle, without which you would not be able fully to understand the science of it, and that is the vaporous condition of the fuel. In order that you may understand that, let me show you a very pretty experiment. If you blow a candle out carefully, you'll see the vapor rise from it. You have, I know,
30
often
seconds.
smelled the vapor of a blown out candle, and a very bad smell it is. But if you blow it out lightly, you'll be able to see pretty well the vapor into which this solid matter is transformed. When I hold a lighted match 2 or 3 inches from the wick, you can observe a train of fire going through the air till it reaches the candle.
10
I'm
seconds.
obliged to be quick and ready, because if I allow the vapor time to cool, it becomes condensed into a liquid or solid, or the stream of combustible matter gets disturbed.
All right, you have a nice weekend. I'll see you tomorrow. All right, bye.
So you do know this one. You have to